Today's daily code problem of the day is step-by-step directions from a binary tree node to another, number 2096. For this problem, we're given the root of a binary tree on a binary search tree, so it's not in order, with n nodes. Each node is uniquely assigned from 1 to n. We're also given an integer start value, which represents the node s, and a different integer destination value, which represents the value of our destination node. Find the shortest path from node s to the ending node t, and we want to generate step-by-step directions in the form of a string with uppercase letters L, R, and U, where L means to move left, R means to move right, and U means to go to the parent node of that node. We want to find the shortest path from node S to node T. So for this, we are going to use a string to first find the path from our root to our starting value. Then we're going to use a string to find the path from our root to our ending value. We're then going to compare those strings and find their last common ancestor. And when we get to the last common ancestor from our start node, we're going to use a U every time we go up searching for the longest common ancestor, as we're going to have to go to the previous node from our start node. So we're going to go 5 is the last common ancestor, so we're going to go from 3 to 1 to 5. So we're going to have a U and a U. 5 is the last common ancestor, so then we can just traverse from the longest common ancestor to our ending node. So then we're going to have a right and then a left. Pretty simple. So we're going to use a string builder to store our paths. Then we're going to have a helper function that is going to find the path from our root to our start node and to our destination node. We're then going to determine the path length. That way we can determine how many U's we need to use to get back to the last common ancestor. And then just simply append the directions to the destination value that we find. So first things first, let's initialize our string builder. So we're going to have a string builder, call it start, and it's equal to a new string builder. Now let's just copy and paste this, and we'll call it end. Then we're going to use a helper function, so we can call this helper function path, and we're going to pass it our root and our start value, so we can find the start value, and we're going to track the path to the start value using our string start. Then let's go ahead and copy this again. Instead of start value, we're going to have our destination value. And instead of our start string, we're going to use our ending string. So let's define this helper function. This is going to be a private function, and it's going to be recursive. So we're going to have a Boolean find path. Sorry, it's just path. We're going to pass a tree node, an integer that is our target, and a string builder we can call path. Yeah, we'll just call it path string because our function is called path. So if our node is equal to null, then automatically we're going to return false. We probably didn't find our target node. Otherwise, if our node.value is equal to our target value, then we can return true. We found it. Otherwise, we are going to have to build our string builder. So we're going to path.append AL. So we're going to test if the left node is the correct node. So if find our path, and we're going to pass node.left, target, and path string. So if that returns true, then we can return true, and that would have built whatever string we needed. It's recursive. Otherwise, If that did not find our solution, then we're going to do path.delete char at path.length. Path string.length -1. So we added an L. This recursively tested. If we go to the left node, can we find our next value? If the answer is no, then we remove the L. Then we're going to try our right side. So path.append our right. Then we're going to do the same thing. If path of node.right target path string, if that returns true, then we simply return true. Otherwise, we want to remove that R because it wasn't to the right of our current node. Then we addressed the two situations it could have been, so we're going to return false. This did not provide us with the node we were looking for. So that's how we're going to identify our paths. Now we are going to identify the ultimate directions by identifying the last common ancestor of the two. And that's going to allow us to build the ultimate directions. So we're going to have a string builder final. This is going to be what we output. That's going to be the final directions, and an int path length. So path length is going to allow us to go back in each of these path strings to find which value they share as a common ancestor. So while our path length is less than our start.length and our path length is less than our end.length and our start.char at path length is equal to our end.path length, end.char at path length So while all those are true, we're going to increment our path length. So path length plus plus. Once we identify the path length from our starting character to our ending character, we are able to determine the moves we need to make to get there. So for int I is equal to 0, as long as I is less than our start.length minus our path length I plus plus. We're going to do final.append a u. So we're appending a u because this is the path length it's going to take for us to get from our starting position to our last common ancestor. And because of that, we're going to need to go to the parent node, and then we could go down from there to find our destination node. In some cases, we might not even have to add u's. We might just continue down the tree. After that, we're going to do the directions from the last common ancestor to the destination's node. So for int I is equal to path length, as long as I is less than final.length. Hopefully that doesn't get messed up. I plus plus. So final dot append end. Wait, I'm using the wrong. Yeah, so this is final.append our end.char at I. But this should be end. So for int I in path length, as long as I is less than n.length, I plus plus directions.append n.char at I. So that will go from the last common ancestor to our final destination. Then we can return our final.to string. So if we run this, passes our test cases, and if we submit it, passes our solutions. So let's do this in Python now. It is, once again, the exact same strategy. So we're going to have start path is equal to empty, end path is equal to empty, self dot find path root start value, and our start path self dot find path of our root dest value and our end path. It's going to have self tree node target path. I'll put a bool. So if node is none, wait, so we have node target and path. If node is none, return false. If node.val is equal to target, return true. Path.append L. If self.find path, node.left, target, path, return true. Path.pop, path.append R. If self.find path, node.right, target, return true. Otherwise, path.pop, return false. Now we just need to find our common path length and identify the directions. So while common path is less than length of start path and common path is less than length of dev end path and start path of common path is equal to end path of common path. While that's true, we're going to do common path plus equals 1. Then we simply need to do directions dot extend u times the length of start path minus common path, then directions dot extend dest end path of common path. And then we just need to return our string joined together. We run this. Pass our test cases. Passes all solutions. So thank you. Follow for more daily LeetCode solutions.